Reviewing functions and relations. So some of the properties of functions. So we want to be able to differentiate when we have a relationship, whether the relationship is a function or not a function. And there's a few tests that we can do for this. So what makes a function? So basically our definition is one input having two outputs is not a function. So one input has to have one output. Okay, so what makes a function? One input maps onto one output. Okay, one element in the domain maps onto one element on the range. Okay, so what does not make a function is when we have one input going to two outputs. And to see this visually, it's a vertical line test. So if I have a graph that looks like this, okay, a vertical line does not pass through twice. If I have a function like this, one input here, 1x, has 1, 2 outputs, so it does not pass the vertical line test. So that's our main test then. Okay, if we have an arrow diagram, we're looking for 1 to 2. 2 to 1 is okay. Okay, so here this is a function. For A, it is a function. Okay, so this 2 mapping onto 1 is okay. This is a situation where we have two different x's mapping onto the same y. Okay, so a parabola is a function because it's two different x's mapping onto the same y. That's okay. Okay, that's okay. It looks like that. But if I have this situation here where I draw my vertical line, it does not pass my vertical line test. Okay, so drawing my vertical line, I have 1, 2, 3 outputs. So my one input x has 3 outputs y. I have 3 y outputs. That's not allowed in a function. So this is not a function. So it does not pass our vertical line test. Okay, 2 to 1. This is what we're looking for. 1 to 2. So 1x maps onto 2 y's. So what ends up happening then is if I were to graph this, my domain is 3. I have a range at 5 and 7, meaning there it is. It doesn't pass the vertical line test. So this is not a function. Okay, so this is not a function. There's no such thing as a horizontal line test, so this is okay. We can have 2 mapping onto 1 y. Okay, so this then becomes a function. This passes our vertical line test. Okay, so that's okay. That's okay. So function notation, the simplest way we can look at function notation is it's another way to write y. And it allows us to differentiate between two y values. There's a 1y here calculation and a different y calculation over here. So that's kind of the basic way. We also want to understand function notation as our input and output. So there is our input. Okay, we need to put it through that function to get an output. Okay, so my input is -2. I put it through the function x squared plus 3. My output works out to be, remember to square the negative, so again it's +4 plus 3 is 7. So my output is 7, or my y value is 7. Okay, so this is my x, my input. There's my f of x, my function. And this is my y, my output. Okay, my domain, my range. When I talk about g, I'm now going to switch to the g function because I want to differentiate between these two different calculations. When I have x plus 3x plus 1, now once I start dealing with expressions, I just got to keep track of my inside expression, the inside substitute into the x in the the equation. So I'm going to write it like this. So my g of x is equal to 2 times x minus 1. Where there's an x, I'm going to input my inside expression. So that's the same as what happened here. I put the negative 2 into there, but I ended up with a calculation. Here I'm just ending up with another expression, so I have to keep track of this. I have to just simplify this now. This is the correct expression. What's implied is I should really make sure that I combine like terms. So it's equal to 6x plus 1. When I have these two different f of x and g of x's, I can replace this f of x with an x expression, and I can replace this g with a g expression. Just be careful though that whenever we do substitutions, especially with minus, make sure you use brackets, because it's easy to lose track of the pluses and minuses when you have a minus outside like this. So combining like terms, I get x squared plus 3 minus 2x plus 1. Okay, this is where most people make their mistake, because it's double negative here. So once I've done the substitution, I have the right expression. What's implied is I always combine like terms. So there's my new expression. F of x minus g of x is equal to this expression here. Here I have to be really careful, because now I have an embedded function. I have an outside and inside. Okay, so I'm going to do my outside. Maybe I'll color code that blue. So there's my f expression. Okay. In fact, maybe I'll just keep this consistent. I'll use green for g. And I have my inside g of x like this. Okay, so my f of x expression is going to be the outside. My g is the inside. So I have my outside expression is going to be x squared plus 3. Again, this does not mean times. It's embedding. It's replacing the x in the original function with the g expression. So the g expression is 2x minus 1. So where there's an x, I'm going to replace it with a g expression. And so there's my substitution. I've done the inside substitution into the outside. So there's an inside function, an outside function. The outside refers to this expression. There's no time. We're not combining with times in here. It's really important to understand that we are embedding a function inside another function. So once I've done that, I've done the substitution part. What's implied is I need to simplify and combine like terms. So I have to FOIL that out. Remember, the squares and minuses don't go together, so I have to multiply here to get this expanded out. And I end up with 4x squared minus 4x plus 4. So there's my final expression for g embedded inside f, or in other words, we say f of g of x.